this problem, we're going to think about changing some amount of ice, initially at negative 15 degrees Celsius, into steam at 103 degrees Celsius. In order to solve this problem, we're going to need to think about the steps we're taking to change our ice into steam. And so it can be helpful to think about a phase change diagram. So let's sketch one out. We know that for water, a phase change or heating curve will have key points at 0 degrees and at 100 degrees. At temperatures less than 0 degrees, we expect water to be solid ice, and that as we continue to add heat to solid ice, its temperature will rise until we reach the melting point at 0. At its melting point, ice takes some heat energy just to overcome intermolecular forces of attraction and convert into water in the first place, during which time its temperature is unchanged. It's only once we've converted all of our ice into liquid water and continue to add heat that we can start to raise the temperature again, but only until we reach the boiling point at 100 degrees Celsius, where again we flatline in temperature as intermolecular forces of attraction between liquid water molecules are overcome. Continuing to add heat to what's now water vapor, steam, continues to raise the temperature once again. In this problem, we're following sections of this heating curve in 5 different segments. We're starting down here at negative 15 degrees Celsius, where we have ice. The first thing that we'll need to do to convert this ice into steam is to first bring it up to its melting point. Step 1. Then we have to melt that ice. That's step 2. Once we've melted ice and converted it into liquid water, we can raise the temperature of that liquid water up to its boiling point. That's step 3. At its boiling point, we need to move it through a phase change, overcome intermolecular forces of attraction, step 4. And then finally, once we have steam, we can raise the temperature of that steam to 103 degrees. 5 steps, 1, 2, 3, 4, 5 different things that we have to do. So 5 equations that we'll need to use. Remember that Hess's law says that adding together heat for individual steps is the same as calculating heat for an overall process. Heats are summative. In order to calculate these heats, we're going to need a couple of equations. Remember from General Chemistry 1 that we can calculate the heat associated with a temperature change, Q, as a function of number of moles, molar heat capacity, and change in temperature, final temperature minus initial temperature. Notice that we're not given number of moles, we're given grams. But we're good at stoichiometry, so we can convert grams into moles quite easily for water, meaning that we'll have 1.304 moles all the way through our calculations. I'll keep more sig figs than I need and round at the end. Notice also that the molar heat capacity is contingent upon the phase of material that we're working with, different for ice, liquid water, and steam. The other equations that we'll need correspond to places on this heating curve where we don't have changes in temperature. When we melt something, we need to take into consideration the enthalpy of fusion, and the heat associated with melting is number of moles times delta H of fusion. Likewise, when we boil something, we take into consideration the enthalpy of vaporization for a substance. Heat is equal to number of moles times delta H of vaporization. We're given those quantities as well in this table. But notice that their units are in kilojoules per mole rather than joules. We'll have to take that into consideration as we move forward. So, let's dive right into this. We're going to solve 5 separate segments along this heating curve to demonstrate how the amount of heat associated with this change works. In segment 1, we're going from negative 15 degrees Celsius as an initial temperature to 0 degrees C. For this purpose, we'll take advantage of this first equation. Q is equal to NC delta T. We already know the number of moles that we're dealing with. The molar heat capacity is given in the table, but we're going to have to recognize we're dealing with ice at this point. That's this molar heat capacity, 37.1 joules per mole degrees Celsius, times the change in temperature, 0 minus negative 15, so just positive 15. Multiplying this all out gives us 725.7 joules. And I'm going to save myself some heartache and just convert that straight away to kilojoules. Divide by 1,000 so that I don't forget to do that at the end and circle my answer so I know where I'm at. All right, that's segment 1. That gets us from negative 15, our starting point, up to our melting point. So now we've got to melt in segment number 2. So let's melt some ice. For this purpose, we'll need to know the enthalpy of fusion. We already have number of moles. The enthalpy of fusion is given in our table as 6.02 kilojoules per mole. So here, multiplying these out, 7.85. Already in my units of kilojoules, I don't have to worry about doing any conversions here. All right, easy peasy, we've gotten through our second segment. Now we need to do our third task, which is bring water, that's now liquid, from its melting point at 0 degrees Celsius to its boiling point at 100 degrees Celsius. Again, we're dealing with a temperature change, so we can use our handy-dandy first equation. We know number of moles, we know our molar heat capacity, this time though for liquid water, given as 75.3. Our temperature change is our final temperature minus our initial, so 100 minus 0. Multiplying all of this out gives us 9,819 joules, and again I'm going to spare myself trouble at the end and just convert to a consistent unit now in kilojoules, 9.819. All right, that gets us through this third leg. In step 4, we boil. For this purpose, we're going to need to take advantage of our enthalpy of vaporization. And again, we have the same number of moles as usual. Our enthalpy of vaporization is given in our table as 40.65 kilojoules per mole, meaning that the heat associated with this segment is 53.0 kilojoules. All right, easy peasy once again. We've got this leg of our journey complete, so we're off to our final stage, which is bringing our temperature from what's now 100 degrees Celsius on up to 103 degrees Celsius. One last time, we'll take our handy-dandy General Chemistry 1 heat equation, substitute in our number of moles, our molar heat capacity, which once again is different because we're dealing with steam now, 36.0, times the change in temperature, final minus initial, 103 minus 100 is 3 degrees, giving us at the end after calculation 140.8 joules. Again, spare us the pain later and convert to kilojoules, 0.1408. All right, well that does it. We've completed the last trip along our heating curve, so now all we have to do is think about summing together each one of these legs, 1, 2, 3, 4, and 5. We'll just add them all. So let's do just that. We'll take leg 1's heat requirement, leg 2's, 3's, 4's, and 5's. All of these were in kilojoules, all had consistent units, and I'll know that I needed 3 significant digits total. That means that I need to keep 1 after a decimal point. When I add all of these together and keep 1 digit after a decimal point, I end up with 71.5 kilojoules. This is how much heat energy is required to change 23.5 grams of ice at negative 15 degrees Celsius into steam at 103 degrees.